Alright, hey y'all, it's Mr. Kyle, Myers Mathematics, and let's just jump into it. We're determining the limit of the sequence, aka the infinite limit as n goes to infinity of a sub n, or showing that the sequence diverges. If it converges, find its limit. Okay, so I meant to only leave up the first line on here, but then I guess I forgot to erase this here. So the first and probably the easiest way to find the limit of something like this is just to notice that it looks a lot like the compounding interest formula. A equals P times 1 plus R over N to the NT power. So the place where the compounding continuously formula comes from, the PERT formula, is that if you're compounding continuously, then n is infinity. If n is infinity, you get the PERT formula. But how does that actually happen? Well, basically, as long as it looks like this, r, whatever the numerator is here, and t, whatever's being times in the power, become the powers of e, and they get times in the power of e. And then, of course, if I drop the p here, if p was 1, then p would be 1 there as well, and I would just have e to the RT power. And that's kind of what I've got going on here. The principal, you could say, is 1, so it's just not visible. And if I take this, I would just need to change it to plus 1 plus, and then it's negative 2 over n to the n times 1 power. So r would be negative 2, and t would be positive 1, so it's e to the negative 2 times positive 1 power, which you could write as 1 over e squared. So this is actually probably the easiest way to get the answer. There is another way to get the answer, and I will show this. It just depends on who the teacher is, who the professor is. They may not need to see this method, but they might. So if you think that they'd be fine with this method, then you can probably just stop it here, because there's not really anything else to talk about. We have the answer. But if you know that your teacher is a little bit more strict, go ahead and pay attention until the end here, because I'll show you the other way to do this, where you're not just relying on the fact that we know that this formula exists, or this set of formulas exist, I guess I should say. So what we would do is we would take the natural log of both sides of the equation. So the ln of both sides. And the reason why that's helpful is then I can take that in and write it as a power. So then it would be this in ln, and I'm going to go ahead and combine this so that it's all one. It's all one fraction here, so that would be n minus 2 over n. Okay, and then what we can do is we can take the limit of both sides. So the limit of the ln of a sub n is equal to the limit of n ln 2 minus, or n minus 2 over n. Okay, so let's do some of the scratch work off to the side here. If we're going to take the limit as it goes to infinity, so the limit as n goes to infinity, then we are usually looking to see if we can use L'Hopital's rule, and we can as long as we rewrite it. If we rewrite it as the ln of n minus 2 over n over 1 over n, then as n goes to infinity, this would be 1, and then the ln of 1 would be 0, and then on the bottom it would be 1 over infinity is 0, so it's 0 over 0, which is indeterminate, which means we can use L'Hopital's rule. If we use L'Hopital's rule, it's a little bit crazy, but we would say it's the derivative of ln is 1 over the thing. 1 over n minus 2 over n would be just saying that it's the reciprocal. Right, so 1 over 2, the reciprocal of 1 over 2 is 2. The reciprocal of 1 over 2 is actually 2. Or sorry, hold on, other way around. If I say 1 over 2, that is equal to 2. The reciprocal of 1 over 1/2 would be a half, which is also the reciprocal of 2. That's what I meant to say, sorry. I'm even getting a little confused here. Reciprocals are a little crazy, so always be careful when you're dealing with those. The derivative of ln of x is 1 over x. So the derivative of this is 1 over this, which is its reciprocal. Then we would also need a times by the derivative of the inside. So the derivative of the inside, it would be 1 minus 2, and then it would be n to the negative 1 power. So that derivative would go to 0. And then if I'm timesing by the power, that would be negative 1 times negative 2 would be positive 2. Times by the power, and then you do power minus 1. So then this would be 2 over n squared. Okay, so we've got that. And then on the bottom, if I take the derivative of 1 over n, that's the same thing as n to the negative 1 power. So that would be negative 1 over n squared. All right, so then from there, we could say that's 2n over, actually, you know what? Let's go ahead and cancel out some of these n's. 1n and 1n will cancel. Go ahead and simplify it a little bit. So 2 over, and then that would be n times n. If I'm going to go ahead and distribute these here, I would distribute the n. So it'd be n times n is n squared. N times negative 2 is negative 2n. All right, so I'm just cleaning up that top part there. Now we can do keep, change, flip. So then this is going to be 2 over n squared minus 2n, which actually maybe that was better to keep it factored out. I don't know. Because that's going to flip and then the n's going to be up there. So actually, yeah, let's do that. So let's just factor it back out again, actually. Because it would be keep, change, flip. Then we can get some n's to cancel again. And then this would be 2n over negative 1 n minus 2. So that looks like that's what that simplifies to. And that actually is not that bad. So what we're then saying is, oh, and then basically what we're saying here is we want the limit, right? So remember, we want the limit of this. The limit as n goes to infinity of this. And now this is a rational function. This is a rational function with a horizontal asymptote because the degree of the top is equal to the degree of the bottom. The horizontal asymptote of this would be negative 2. So this is literally just equal to negative 2. Can you guys see that? Yeah, you can. Okay. So this whole thing is literally equal to negative 2. And then what we can do is we can change the form back into an exponential because what we have is the ln, which is a log base e, right? And ln is a log base e. So then I can say so the base stays the base and the other switch place, right? So e to the negative 2 power, the base of e to the power of this is equal to this, and it's still got that limit there. So this part's a little tricky, and I'm not even like 100% sure why that works, but it does. So yeah, so that's the other way to get the same answer is now we know by using logarithmic, not logarithmic differentiation, which you may be familiar with, but the logarithm method of finding limits is another way to do this one. And we get the same answer, e to the negative 2 or 1 over e squared. So hopefully that was helpful. Yeah, so go check out the 5 math mistakes everyone makes and how to avoid them. That is on my website, myersmathematics.com, which is down in the description below. And I'll catch you on the next video. Blessings, y'all.